Welcome to all. In the previous video of differential geometry, we have seen what is speed of a curve. So, yes, curve is the locus of a point which is moving with respect to the origin, like the motion of position vector is observed in terms of a curve. We have seen about speed of a curve. Now we will see what is arc length of a curve. So, as curve is as the point P is moving, means the position vector is moving. Due to that, some distance is covered by the point on the curve. So we can see the distance travelled by the moving point is determined by the repeated summation of speed with respect to time. So that is, we have, since we know that velocity is equal to distance by time, or we can write, actually it is displacement by time, therefore speed is equal to distance by time. If I am interested in distance, then distance is equal to speed into time, because distance is a length function, means it will give the length of the moving object. Yes, we are interested in arc length of a curve, and we can use the formula distance is equal to speed into time. So if it is a curve in E3 and P is a point on the curve, as we have seen the curve as a locus of the point P in terms of the position vector as a vector through OP. Now if the point P moves on the curve, then it covers some distance. So this distance is nothing but the arc length, which can be seen in terms of arc length function. If we want to find the length of the curve between 2 points, suppose it is a point A and it is a point B, then if we point to point, what is the length of the curve in between these 2 points, that can be found out with the help of this formula, speed into time. Yes, we are finding the length, we have to sum the distance in each instant. So this can be achieved through the integration process. If suppose, thus we can write arc length of the curve from the point A to B, from at this, suppose at a time instant t, from t is equal to A to B, is given by, so where to where we are taking from A to B, so this is A to B. Speed into time, speed is in terms of norm of the velocity vector into time, means it is very small time, change in time is dt. So this is nothing but the arc length of the curve which is moving in E3 between the limits A to B. This equation we can call it as arc length function. As usually distance is viewed in terms of parameter s, therefore arc length function of a curve alpha in E3 is given by s of t, because it is varying with respect to time t. So s of t is equal to A to B norm of alpha dash of t into dt. So this is how we can find the length of the curve between the two limits, provided we know the speed of the curve. So this is how we can calculate arc length with the help of arc length function given in terms of integration expression. So yes, we have seen in case of reparameterization of curve, we are not thinking about velocity of the curve, we are just thinking about root of the curve. So whatever may be the velocity, we are interested in the root followed by alpha should be same as root followed by beta. In case of, if alpha is the original curve and beta is the reparameterization, we think about only the root of the curve, not interested in speed of the curve. Therefore we are not taking into account of the speed of the curve. Therefore we sometimes what we make is we make the speed of the curve as unity. Speed as unity means speed is 1 unit. So as we are ignoring speed, therefore one way to ignore the speed of a curve is reparameterize the curve in such a way that the reparameterized curve has unit speed. What we can write is, one way to ignore the speed of a curve, as we are not taking into account of speed of a curve in case of reparameterization, just we follow only root of the curve. Speed of a curve alpha is to reparameterize it to a curve, so new curve is beta, such that beta has unit speed. So as we are not interested in speed of the curve, whether it is original curve or it is a reparameterized curve, we are interested only in root followed by the curve. Therefore, the only one way to ignore the speed of the curve is to reparameterize the curve alpha to the new curve beta, such that the speed of the reparameterized curve is 1. So what we can write in terms of expression, that is nothing but norm of beta dash of s should be equal to 1. So beta of s is a reparameterized case, beta dash means it is a velocity vector. The norm of velocity vector of the reparameterized case should be having unit value. So this is how, if we don't think about the speed of the curve, then the best way to reparameterize the curve is that it should be reparameterized in such a way that the reparameterized curve will have unit speed. The expression is given in terms of norm of the velocity vector of the reparameterized curve. Now we have one more concept called regular curve. As we have seen, curve is a function from I to E3 and I is an open interval. This curve alpha is said to be regular if velocity of alpha will never be 0. Velocity of alpha will never be 0 for all t belongs to the open interval. So that is, velocity vector means alpha dash of t is not equal to 0 for all t belongs to I. So a curve alpha in E3 is said to be regular if its velocity is never 0 for all time t in the open interval I. We can state it another way as, this is first definition, alpha from I to E3 is said to be regular if alpha has no critical points. No critical points indirectly mean alpha dash of t is not equal to 0 for all t belongs to I. So geometrically what we can say is, alpha from I to E3 is said to be regular if alpha has no corners. Alpha has no corners. If it has a corner, then velocity becomes 0. So if it is having any corner, then here velocity becomes 0. Therefore, for a curve to be regular, its velocity never be 0 or it has no corners. So this is how we can see when a curve is regular. Now moving further, so we will have a result on regular curve. We will take it as theorem. If alpha is a regular curve in E3, then there exists a reparameterization of alpha, reparameterization beta of alpha, such that beta has unit speed. What it says is, if alpha is a regular curve, then there exists a reparameterization beta of alpha such that the speed is unit for beta. So as if alpha is any curve, then obviously there is a reparameterization, but it need not be having unit speed. But if alpha is a regular curve, surely there will exist a reparameterization beta such that it has unit speed. So for regular curve, there must exist there will surely exist a reparameterization beta such that its velocity is unity. Its speed is unity. Sorry, its speed is unity. So first we will see how it is possible. We have a curve alpha from I to E3 is a curve and is regular. Let beta of s is the reparameterization of alpha. So since beta is a reparameterization, therefore we can write beta of s is equal to alpha of h of s, where h is a function from open interval to, which is open interval, and I is a open interval, which is a differentiable function. So with the help of h we will reparameterize alpha, and alpha is from I to E3. Now we are interested in finding speed of beta. Now for speed of beta, we can differentiate beta with respect to s. Therefore we can write beta dash of s is equal to alpha dash of h of s into h dash of s. This is the result in terms of velocity of beta alpha dash of h of s into, we can write dh by ds at s. Now as we are interested in speed, we have to take norm for velocity vector of beta. So norm of beta dash of s is equal to norm of alpha dash of h of s into dh by ds. So as dh by ds is a scalar number, means it is a number, so but alpha dash is a vector, therefore we can write it as norm of alpha dash of h of s into dh by ds. So we are just neglecting s for our convenience. Now what we can write is, so reparameterization of alpha means here the variable, suppose alpha of t is the original curve, yes, t is replaced in terms of another variable s, therefore we can write it as alpha of h of s can be rewritten as h of s can be rewritten as alpha of, so t of s. So I don't want to change the parameter t, so just want to change t in terms of the new variable s. So it is possible to take this as, because h is a differentiable function which for which we can take any other notation. Therefore beta dash of s is equal to alpha dash of t, alpha dash of t of s into dt by ds. So in order to get the norm of beta dash as unity, we should have, instead of alpha dash of t of s, so norm of this should be, if it is equal to ds by dt, then we will have norm of beta dash should be 1 only when, so this ds by dt and dt by ds should be reciprocal of one another, means reciprocal of one another or inverse of one another. So this is possible when ds by dt and dt by ds are inverse of each other. We will see whether they are inverse of each other or not. Therefore as s is inward, we have to take arc length function. Consider the arc length function s of t is equal to a to t alpha dash of t into dt. So here I have taken lower limit as alpha and upper limit as variable t. So here a is a member of I, open interval I. So this a, we can fix a point and we will find the length with the variable t, means if it is a curve and it is a lower point, and we can take the length from the point a to anywhere, so that upper limit is variable and lower limit is fixed. This fixed lower limit is called base of the arc length function of curve, or s of t, the arc length function is based at alpha, at a, sorry it is a. So now arc length function s of t is equal to a to t alpha dash of t into dt. So I want the norm of alpha dash, therefore I will just differentiate s with respect to t, therefore we can get ds by dt is equal to alpha dash of t. So yes, alpha is a regular curve, alpha dash of t is not equal to 0 for all, therefore ds by dt is not equal to 0, but s is arc length function. This implies s is, the function should be greater than or equal to 0, but it is not 0, therefore we can write ds by dt is strictly greater than 0. Yes, ds by dt is strictly greater than 0 and s is the arc length function. There will exist inverse for inverse of s. So inverse of s exists. Yes, s is a function of s of t. The inverse of s should be, inverse will be t, and t is a function of s. So derivative of this function will be dt by ds. Yes, ds by dt is greater than 0. We can take the reciprocal of that. Reciprocal of ds by dt is also greater than 0. This implies dt by ds is also greater than 0. So both are greater than 0. So therefore no need to take the reciprocal of one another. Now we will substitute the inverse of ds by dt in the expression beta dash of s is equal to norm of alpha dash into dt by ds. Therefore that will become norm of beta dash is equal to norm of alpha dash of t of s into dt by ds. So norm of alpha dash is equal to ds by dt into dt by ds. As ds by dt and dt by ds are reciprocal of one another, we can, both will cancel each other, therefore beta dash, norm of beta dash of s is equal to 1. This implies beta has unit speed. This is how, for a regular curve there should exist, or there will exist a reparameterization beta such that it has unit speed. So this is how the proof follows. We will see examples on speed of a curve and arc length function, and also unit reparameterization in the upcoming videos. Till then, keep watching. Thank you.